Let us look at the benzylic bromination. So, similar to the allylic bromination, in the case of benzylic bromination with NBS, here also the chain carrying radical is actually the bromine atom and not the succinimidyl radical. So, this is what we have seen whenever we are running a NBS bromination, the chain carrying radical is basically the bromine atom. So, once the bromine atom is formed, so what the bromine atom does is this actually abstracts a beta hydrogen. So, when it abstracts the beta hydrogen atom, HBr is formed and that is the one which is being eliminated, and then we end up with a radical on this benzylic carbon atom. So, that is where we see the benzylic carbon is having the radical, and this radical can now get into resonance with the aromatic system. So, here we have the ortho position and para position and the ortho position. So, in other words, we can actually say a very stable benzyl system is having this radical electron currently. And finally, what happens is when the bromine atom reacts with this alkyl this benzyl radical, that is, this is generally called as the R dot when we talk about. So, this R dot reacts with bromine to give bromine plus Br dot. So, Br dot is formed as the second product. So, this is what is the termination reaction finally, and this bromine radical is again used in the initial step. So, the bromine radical undergoes a cyclic system of again and again it can actually react with another one more molecule of the starting material, and we end up with our final product. So, the minion asks question, sir, in the previous slide there are many resonance structures, why the bromine radical does not add to the ring? So, this is a very good question. If we go back, we have various especially we have 3 resonance structures where the aromatic system is having the radical. So, when we do this reaction, basically in the propagation step what happens is the bromine radical abstracts a hydrogen atom. So, this is the most crucial one, and which hydrogen will be abstracted is leading to the final product. So, we already know the benzylic CH bond is the weaker than the phenyl CH bond. So, that is the reason benzylic radical is formed. So, we are perfect up to this level. Now, when this benzylic radical is in resonance with the aromatic system as shown here, if bromine now adds to this particular radical in the aromatic system, we end up with a product as shown here. So, in this particular case we completely lost the aromaticity. So, this is a very high cost for that molecule, because this molecule is going to be less stable compared to this particular aromatic system. So, in the case of benzylic bromination, this product is more stable compared to this product where we have the exocyclic double bond and the bromine is added to the aromatic system. So, here we lost aromaticity. So, this product is going to be highly less stable compared to the benzylic product. So, that is the reason this product is not formed. And when we look at the application of benzylic bromination, the benzylic bromination, this bromine can be replaced by various other nucleophiles, like SN2 type reaction can be replaced by the hydroxy group or acide group or thiol group. And in the case of tetraline also, this can be converted into naphthalene using this kind of reaction by forming a bromination. So, when we do the first allylic bromination, we end up with a bromine added here, and this bromine can be eliminated by minus HBr, leads to this particular double bond, and then the second bromination occurs here, and which can also be eliminated as minus HBr to give the second alkene. So, in other words, tetraline can be converted to naphthalene by allylic or the benzylic bromination reaction. So, these are some of the applications of benzylic bromination. Here another example given for the application of benzylic bromides in the synthesis of various product. So, here benzyl bromide reacts with the famous Williamson ether synthesis to give a ether as shown here, and this hydroxy group can be converted to bromine, and this bromine again undergoes the reaction. In this kind of the repetition of this kind of reactions are called dendrimer synthesis. So, we start from one single unit, we are building up or adding multiple units to the system. So, we end up with the generation 1 or the generation 2 products, and this generation 2 product can be further elaborated to give these kind of polybenzyl ether dendrimers as shown here. So, these are some of the applications of benzylic bromides in organic synthesis. Let us move on to the next topic, that is alkyne. So, before we start our alkyne study, let us recall what we have studied earlier about Bronsted-Lowry theory. So, we call acids and bases based on protons. So, any compound that can transfer a proton to any other compound is called an acid. So, this is the one thing you have to remember, anything that can actually transfer a H plus is called an acid, and any compound that accepts a proton is a base. So, this is the Lowry-Bronsted theory for acids and bases. And when we talk about water which can either accept a proton or give a proton, these are called amphoteric compounds.